So we're going to start off today by looking at number 19 from the homework last night, which was on page 473. We're asked to find the secant of negative pi over 12. Oftentimes it might be, and so, sorry, let me back up here for a second. We're going to use our sum or difference identities to figure this out. So first of all, we only have sum and difference identities for sine and cosine and tangent. So let's write this in terms of cosine first of all. And it helps me often to convert to degrees when I'm thinking about what this could be a sum or difference of. Right, because I have to find two special angles that have a sum or difference of negative pi over 12. Probably a difference if it's negative. So negative pi over 12, well, 180 divided by 12 is negative 15, right? And the one I can think of off the top of my head is 30 minus 45, right? So this could be the same as 1 over cosine of 30 minus 45. And so that'll be 1 over cosine 30, cosine 30 sine, let's go to this in the next page here. Of course I did that. Yeah, let's go ahead and put this down in the next line since we're losing it here, space-wise. All right, so we'll get 1 over cosine 30, and then I go ahead and mess that one up right away. Cosine 30 cosine 40, 5, plus sine 30 sine 45. Okay? All right, and so we'll get 1 over all that. So cosine 30 is square root of 3 over 2. Cosine 45 is 1/2. Sine 30 square root of 3 over 2 sine 45 is 1/2. Sorry, cosine 45 is square root of 2 over 2. And sine 45 is square root of 2 over 2. And sine 30 is 1/2. So I sort of messed that all up. Let's go ahead and fix that. Sine 30 is 1/2. Sine 45 is square root of 2 over 2. All right, there we go. So we'll end up with 1 over square root of 6 over 4. Right, so we'll end up getting square root of 6 plus square root of 2 over 4 if we simplify all that. And if we go ahead, I'm just going to go ahead. So avoid having to use another page here. Let's go ahead and put this up here. And we rewrite this as 4 over square root of 6 plus square root of 2. Right. Last thing we should probably do is to rationalize the denominator. So that we get 4 square root of 6 minus 4 square root of 2 over 6 minus 2 is 4, which will just give us square root of 6 minus square root of 2 when it's all said and done. All right. So there we go. Square root of 6 minus square root of 2 for secant of negative pi over 12. So once again, expressing it as a sum or difference of angles, of special angles whose values we do know, we can figure this one out. Today we're going to look at the double and half angle identities. It does not look like half. Right, the double and half angle identities, which are very easy to derive once you have the sum and difference identities. So for instance, we know that the sum of two angles, let's call them alpha and beta, is equal to sine alpha cosine beta plus sine beta cosine alpha, right? Now, what if we just made those the same angle? What if we went ahead and just substituted theta in for both of those, right? Then we're going to get sine theta cosine theta plus sine theta cosine theta. And that's just going to combine to be 2 sine theta cosine theta. And theta plus theta is just 2 theta, right? So that is what we call the double angle identity for sine. Sine of 2 theta, double whatever theta happens to be, is 2 sine theta cosine theta. So there's one of our first identities. And we are going to do the same thing with cosine. So this is the double angle for sine. It's a sine double angle. We know that cosine of the sum of two angles, let's say alpha plus beta, is going to be equal to cosine alpha cosine beta minus sine alpha sine beta. Right? So once again, if we go ahead and substitute theta in for both of those, just some angle theta, right? We'll end up getting cosine theta cosine theta minus sine theta sine theta. So we have that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. So this one looks strikingly similar to the Pythagorean identity. It's not. It's completely different from the Pythagorean identity, right? But it looks a lot like it. So with the Pythagorean identity, we had sine squared plus cosine squared equals 1. This one says that cosine of double of an angle is cosine squared theta minus sine squared theta. Now, even though this is not the Pythagorean identity, and we shouldn't confuse it with the Pythagorean identity, we can use the Pythagorean identity to write this in a couple different forms. So first of all, the Pythagorean identity says that, I'll put the Pythagorean to the side, that cosine squared theta plus sine squared theta equals 1, right? That's my Pythagorean identity. So that means cosine squared by itself is equal to 1 minus sine theta. So what we can do here is we can write this in a couple different forms. We can say cosine of 2 theta is equal to 1 minus sine squared theta minus sine squared theta, right? If I go ahead and substitute 1 minus sine squared theta in for cosine theta right here, right? And then I can just simplify that to say 1 minus 2 sine squared theta. So this is the basic one, and this is another form of it, 1 minus 2 sine squared theta. And we can do the same thing with sine. We can say sine squared theta right here is just equal to 1 minus cosine, right? And do that substitution as well to get that cosine of 2 theta is also equal to cosine squared theta minus 1 minus cosine squared theta. And we'll end up with 2 cosine squared theta minus 1. So that is yet a third form. So there's 3 different forms. For whatever, because of the way the cosine double angle identity works out, there's 3 different forms that often come up, whereas with the double angle identity for sine, really only one sort of pops up. Okay? So those are your double angle identities. Those are all 4 of them right there that we just covered. These are our cosine double angle identities right here. We have 1, 2, and 3. Okay? All right, so for instance, if I said if sine theta is equal to 3/5, and I told you that the angle theta was between pi over 2 and pi, and I asked you to find the exact value of sine 2 theta. right? So you know what sine theta is equal to, right? And you have angle theta being between pi over 2 and pi, meaning it's in the second quadrant. Figure out, using the identity we just established, what sine 2 theta is equal to, please. Go ahead and take a shot at that. This is one of these classic cases when we want to go ahead, whoops, and draw a better coordinate grid than that. Want to go ahead and draw our unit circle. Right. Open up our angle, which we know is going to be in the second quadrant. Whoops, I don't know why I just drew that one. So our angle is in the second quadrant, right? And so we can make our reference triangle, and if sine theta is equal to 3 over 5, then actually we're going to call this, instead of being a in the unit circle, we're going to have this just be in a circle of radius 5, right? And we'll have a radius be 5. And the y-coordinate of the point on the circle will be 3. And the x-coordinate we're going to have to figure out. So we'll get x squared plus 3 squared is equal to 5 squared. And if you're familiar with this Pythagorean triple, you'll know that x has to equal 4 in that instance. Right, so x is 4. And we'll go ahead, and we know that that means that cosine theta then is going to be equal to 4 over 5. And sine 2 theta using our identity is equal to 2 cosine theta sine theta. So that's going to be equal to 2 times 4/5 times 3/5, which is going to be 24 25ths. 24 25ths. Okay. Yep. Oh, and I'm sorry, yes, so sine is positive, and yeah, cosine should be, that was a mistake I made, cosine should be negative in the second quadrant because the x-coordinate of that point is negative. And so yes, cosine should be negative, and so it should be negative 24 25ths. I'll just rewrite that. So we should have negative 24 over 25. Okay. Why don't you go ahead for me and develop a formula for the double angle for tan using the sum difference identities that you already have. So go ahead and develop a formula for tan 2 theta. So what's the double angle formula for tan? So you might have to look up the sum or difference identity for tan to be able to do this one. So for this one we need to use the double angle formula for tan. Sorry, we're going to use the sum formula, I should say. So we're going to break this apart and treat it like a sum, theta plus theta. And the sum formula for tan is going to be tan theta plus tan theta. Normally these would be different angles, but they're the same in this case. Over 1 plus tan theta times tan theta. Right, and so if we simplify that, that'll be 2 tan theta over 1 plus tan squared theta. So we just used the sum formula for tan. Wrote this as theta plus theta. Okay. In this next example here, I want you to develop a formula for the triple sine of the triple angle, so sine 3 theta, and you're going to use the same general strategy that you used for sine we used for sine 2 theta earlier, right? Definitely going to involve the sum formulas. So go ahead and give that a shot. All right, so for sine 3 theta, what we can do is once again we're going to use that same strategy. Right? Let's write this as sine of theta plus 2 theta. It's not coming across very well. There we go. The sine of theta plus 2 theta, and we'll use the sum formula for sine. So it's going to be sine theta cosine 2 theta plus sine 2 theta cosine theta. So what do you think we should do here from this point? Should we go ahead and apply our double angle formulas for cosine 2 theta and sine 2 theta? So sine theta times cosine 2 theta. Let's use the one, let's get this entirely in terms of, because we have choices for cosine 2 theta, right? There's only one double angle formula for sine, but there's a whole bunch of them for cosine. So I'm going to use the one that is 1 minus 2 sine squared theta. And for this one over here, I don't have a choice. It's just going to be 2 sine theta cosine theta times cosine theta, right? When I use the double angle formula for sine. And so I'll end up with sine theta. You know what, actually, I take that back. I am going to go ahead and instead just use the regular old formula for cosine 2 theta, the first one, which is cosine squared theta minus sine squared theta. Right, and so let's go ahead and distribute that. We'll get sine theta cosine squared theta minus sine cubed theta plus 2 sine theta cosine squared theta. And so that one we can combine, so we'll end up getting 3 sine theta cosine squared theta minus sine cubed theta. Right, so we have it all in terms of theta at least, even, and we have some higher powers there of sine and cosine, right? So that's one thing that we can do. And there's actually more than one way to do it. I could also, I could go ahead and apply some other identities there too, but I'm just going to leave it as is for now. Right, and so there's not always one answer for these questions, and it all depends on what we're trying to do and what we're trying to accomplish. In this case, it makes sense to get it all in terms of theta. We don't want any 2 thetas or 3 thetas going on here. It's entirely in terms of just 1 theta, so that makes things easier for certain situations. And so there are some other formulas that, there's some ways that we can use the double angle formulas that are going to be really helpful in the double angle formulas are good for breaking double angles down into single angles, right? If we have sine 2 theta or cosine 2 theta and we want to express that in terms of just a single theta, that's one use they have. But they can also be used to create what we call power reduction formulas, which are actually very useful in calculus for specific things. So power reduction formulas. So let's look at our cosine double angle, one of our cosine double angle formulas, which is 1 minus 2 sine squared theta. So we have this right now solved for 2 theta. But what if instead we went ahead and solved this for sine squared theta, right? So let's go ahead and do that. So we'll end up getting cosine 2 theta minus 1 is equal to negative 2 sine squared theta. And then if we go ahead and solve for sine squared theta by dividing the whole thing by negative 2, we'll end up getting 1 minus cosine of 2 theta all over 2. Right, so like I said, once again, this is a useful formula because if we have something in terms of like sine squared and we want to get it in terms of something where there's no powers of sine or cosine, that's very useful in that sense, right? And that's something that's going to be useful in calculus, like I said before. So this is the power reduction version of the double angle formula for cosine. Now if I want to, and I'm going to do the same thing now, I'm going to use the cosine squared version of the double angle formula for cosine, which is cosine 2 cosine squared theta minus 1. Right, and then if I go ahead and solve for cosine squared theta, I'm going to get 1 plus cosine 2 theta over 2. So now we have a way of expressing sine squared and cosine squared in terms of a formula that doesn't involve a power of a trigonometric function, right? And when we have powers of trigonometric functions, that does complicate things in certain instances. So it is nice to have these power reduction formulas. And then lastly, we can do the same thing with tan squared theta. Right, so we go to the next page here. For tan, we know that's just the same as sine squared theta over cosine squared theta, and we'll just use those two formulas that we had before. So sine squared theta was 1 minus cosine 2 theta over 2 divided by 1 plus cosine 2 theta over 2. And so we'll end up with, if we go ahead and multiply this, 2 minus, well, the 2's will just cancel, right? The 2's are going to cancel, and so we'll just end up with 1 minus cosine 2 theta over 1 plus cosine 2 theta. Okay? So that is our power reduction formula for tan squared theta. So if we want to take something and reduce it so that there's no more powers, those are the formulas that we can use for that. And we can also use those to establish the specific identities as well. Okay, so power reduction formulas. So I want you to establish a formula. Whoa. For cosine to the 4th theta that doesn't involve any powers of trig functions greater than 1. So establish a formula for cosine to the 4th theta that doesn't involve any powers of trig functions that are greater than 1. Okay? And you're going to use these power reduction formulas in the process there, and you might have to use some other formulas as well. Just keep trying to reduce the powers until you have no powers left. So cosine to the 4th theta, here's the trick we're going to use first. We're going to write this in terms of cosine squared theta squared. Anyone do that? So far, so good, yeah? And so cosine squared theta, we know from our power reduction formula, is 1 plus cosine 2 theta over 2. So we're going to go ahead and square that. Right, so that will get 1 plus 2 cosine 2 theta plus cosine squared 2 theta all over 4. Sorry, not 2. Right, so we're getting there. We only have a squared power now, so we're going to do the same thing twice here. And we're going to go ahead and do the the reduction formula for cosine squared 2 theta. So we're going to end up getting 1 plus 2 cosine 2 theta. It's all going to be over 4, I guess. All over 4. Right? And then cosine squared 2 theta. We'll apply our power reduction formula there. So we will get plus 1 plus cosine, and then we're going to have 2 times 2 theta there. So it's going to be cosine 4 theta all over 2, of course. Right, and then we got to go ahead and clean that all up. So we'll get 1/4 plus, and so what we're going to have to do here is just multiply the whole thing by 2. I'm going to have to do this on the next page here, so let's go ahead. So what I'm going to do next, I'm just going to multiply the top and the bottom of this expression by 2 to get rid of that fraction in the numerator. And so on the next page, if I can remember this, actually, let me try a little trick here, which is probably not going to work. No, you can't do that, I don't think. All right. Anyways, on the next page, we have 2 plus, would it be 4?
Yeah.
Cosine 2 theta plus 1 plus cosine 4 theta. And this is all going to be over 8, right? And then if we go ahead and reduce this, we'll end up with, I'm going to break it apart, 1/4 plus 1/2 cosine 2 theta. Whoops. 3/8. I apologize, because there was the 2 and we should combine the 2 and the 1 here to give me 3. So we'll end up with 3/8 actually. Plus 1/2 cosine 2 theta plus cosine 4 theta, or 1/4 cosine 4 theta. So we've got this entirely in terms of lower powers. Sorry, that's 1/8. I don't know where I can put the 4th there. Of all powers of 1 of cosine. So we've power reduced cosine to the 4th theta there, which is useful. Okay. All right. Let's go ahead here and develop some more formulas. So we're going to start off, to develop the half angle formulas, we're going to start off with the double angle formulas, right? So for instance, we have cosine, we'll start off with the power reduction formulas actually. So we have cosine squared theta, right, is equal to 1 plus cosine 2 theta over 2, right? So, if I go ahead and do a substitution, let's make a new angle called alpha and have that be equal to 2 theta, right? So we're just going to make up an angle and we're going to define it to be equal to 2 theta. And now I'm going to go ahead and do a substitution here. So we're going to get everything in terms of alpha now. So we have 1 plus cosine alpha over 2, and over here, theta, of course, then is going to be equal to alpha over 2, right? So cosine squared of alpha over 2 is equal to 1 plus cosine alpha over 2. And so if I want to figure out what the half angle is going to be equal to, it's just going to be the square root, plus or minus square root of 1 plus cosine alpha over 2. Right, so now I have a formula for finding half, the sine or cosine of half of an angle, right? Which can also be useful. So cosine of the half angle, of course, there's also, and they can be derived the same way, but I'll just write them. So sine alpha over 2 is then going to be equal to plus or minus the square root of 1 minus cosine alpha over 2, right? And tan alpha over 2 is going to be equal to plus or minus the square root of 1 minus cosine alpha over 1 plus cosine alpha. And these all were derived directly from the power reduction formulas for cosine, sine, and tangent. All right, so, like the following, to find, let's say, cosine of 15 degrees and sine of negative 15 degrees, you're going to go ahead and use those formulas, right, to do that. So go ahead and use the half angle formulas to find the exact values of cosine 15 and sine of negative 15, please. So cosine 15, right, same as cosine of 30 over 2. And so using the half angle formula we developed, that's equal to plus or, it's going to be equal to plus or minus the square root of 1 plus cosine 30 over 2. Now, 15 degrees, should cosine be positive or negative in that situation? Positive, so we're just going to get rid of the negative one of those. The only one that makes sense is the positive one. And so we'll get the square root of 1 plus cosine 30, which is square root of 3 over 2, all over 2, right? And so we'll end up with square root of 1/2 plus square root of 3 over 4, right? And at that point, we can just sort of, well, we can go ahead and combine it into 1, right? So we end up getting 1/2 is 2/4, right? So we'll get the square root of 2 plus square root of 3 over 4, which just gives us 2 plus square root of 3 over 2. So we have a square root inside of a square root, which is never ideal, but there's not really anything you can do about that. Sine of negative 15 is the same as sine of negative 30 over 2, right? And so we'll end up getting, and then, so sine of negative 15 has to be negative or positive? So we're going to take the negative square root of 1 minus cosine of negative 30 over 2, right? And so we'll end up getting negative square root of cosine negative 30. It's going to be negative square root of 3 over, it's going to be still positive square root of 3 over 2. All right, all over 2. And so we're going to get the same exact thing more or less, except it's going to end up being negative square root of 2 plus square root of 3 over, sorry, 2 minus square root of 3 over 2. When we go ahead and simplify on the inside there and take the square root of the bottom, as we did before. So there, sine negative 15, cosine 15. So we can use the half angle formulas to evaluate angles that we couldn't figure out previously. We know what cosine or sine is equal to, and we have to figure out what the other trig functions are. So if cosine alpha is equal to negative 3/5, right, and alpha is between pi and 3 pi over 2, whoops, pi and 3 pi over 2, right, find the exact value, right, of, let's say, tan of alpha over 2 using our half angle formula. Okay, so go ahead and take a crack at that. If cosine alpha is equal to negative 3/5, then find the exact value of tan alpha over 2 using our half angle formula. Alrighty, so cosine alpha is equal to negative 3/5. So what's nice about this is we know that, first of all, if alpha is between pi and 3 pi over 2, right, then alpha over 2 has to be between pi over 2, right, and 3 pi over 4, so that that original inequality holds. Right? If we divide the whole thing by 2, we get that. So alpha is going to be in what quadrant then? Third? What's pi over 2? What's 3 pi over 4? Yeah, so that's in the second quadrant. So we're in quadrant 2. Right, and so if I want to find tan alpha over 2, first of all, tangent is positive or negative in quadrant 2. So when we're going to use the tan formula, we want to take the negative version, and so we get 1 minus cosine alpha over 1 plus cosine alpha. We know what cosine alpha is, so we get 1 minus, which ends up being plus 3/5 over 1 minus 3/5, right? And so we'll end up with 3/5 plus 5/5 is 8/5 over 1 minus 3/5 is 2/5. The 5's cancel. And so we get square root of 8 over 2, which is just, I feel like I screwed something up. No, that's right. And sorry, I needed the negative version, so I need to keep that negative. And square root of 8 over 2 is just square root of 4, which is 2. So negative 2 is the value of tan there for alpha over 2. So we don't even have to do any unit circle or circle of other radius stuff because the formulas involve, they all involve cosine and we were given cosine. So that's convenient, of course. So the half angle formula for tan is a little bit clumsy just because it involves this, a square root tangent, which we can go about in deriving. So, and that is that tan alpha over 2 is equal to 1 minus cosine alpha over sine alpha, which we showed earlier in like a while ago when we first started dealing with identities, that that's equal to sine alpha over 1 plus cosine alpha. We found that by multiplying the top and the bottom by the conjugate. If we remember back to that one. So let's go ahead and just show that this is actually true. Right, if we start off with 1 minus cosine alpha over sine alpha, right? 1 minus cosine alpha by the half angle formula, right? We know the half angle formula for sine gives us square root of 1 minus cosine alpha over 2. So if I go ahead and square it, I'll get, this is going to be equal to sine squared, I have the wrong side of the thing, sine squared, because I have the eraser, how about that? Sine squared alpha over 2 times 2. So 2 sine squared alpha over 2. So equals 1 minus cosine alpha. I just got that directly from the half angle formula for sine, right? Because we had sine of alpha over 2 is equal to plus or minus square root of 1 minus cosine alpha over 2. So if you just go ahead and you solve for 1 minus cosine alpha, you get 2 sine squared alpha over 2, right? And on the bottom, right, sine alpha, right, I'm going to go ahead and use my double angle formula for that. So sine of sine of 2 theta, we remember, is equal to 2 sine theta cosine theta, right? And so if I write this in terms of alpha, let's say alpha is, equal to 2 theta. So sine theta is equal to 2 sine alpha over 2 cosine alpha over 2. Doing that same substitution I did before. Right, and so we end up getting 2 sine alpha over 2 cosine alpha over 2. Thanks to this situation right there. And we go ahead and reduce that. We get the 2's cancel, and one of the sines cancels, leaving us with sine alpha over 2 over cosine alpha over 2. Whoops. So sine alpha over 2 over cosine alpha over 2, which is the same as tan alpha over 2. So I've verified that identity now. This is a tricky one to verify, which is why I did it out and didn't have you guys do it. But this is another half angle identity that I can use for tangent. Right, which is sometimes more convenient because it doesn't involve a square root with the plus minus. It's a simpler expression for tan alpha over 2. Let's do one last quick question since we sort of started a little late here. Let's finish off with a word problem because it's nice to work those in every now and then. So we have a situation where an object is propelled upward at an angle of theta to the horizontal with an initial velocity of v0 feet per second. If air resistance is ignored, the range r, the horizontal distance the object travels, is given by the function r theta. So the first thing you want to do is use some trigonometric identities, to show that r theta is equal to 1 over 32 v squared sine 2 theta. So that's just a verification of an identity. And secondly, Find the angle theta for which r is a maximum. So you'll use what you know about sine to answer that question. You don't have to use your calculator, right? You just have to use what you know about the sine function to answer that question. So go ahead and give that a shot. All right, so let's start off with part A here and show that this is actually the case. So we have 1/16, we're going to start with 1/16 v naught theta sine theta cosine theta. So, whoops, let's get the theta in there. So sine theta cosine theta, which does that remind you of an identity that we've talked about recently? The double angle for sine. So sine 2 theta is equal to 2 sine theta cosine theta, meaning, right, sine theta cosine theta then is equal to sine 2 theta over 2. So if I substitute sine 2 theta over 2 in there, I will get 1/16 v naught squared sine 2 theta, whoops, sine 2 theta over 2, which will give me 1/32 v naught squared sine 2 theta. So I've shown that how that can be derived. Now, for part B, the expression 1/32 v naught squared sine 2 theta is going to be at it. So, and v naught theta is a constant, by the way. So no matter what that happens to be, the maximum is going to depend on sine 2 theta. So when does sine reach its maximum? What's the maximum value for sine? Go back to what you know about the range of sine. Sine goes from where to where? What does it oscillate between? Sine goes down to what and up to what? Over and over again, forever. -1 to 1. So what's its maximum value? That occurs when theta equals, when 2 theta equals what? Where does it get to 1? There's only one place between 0 and 2 pi that does that. 90. So yeah, so when 2 theta is equal to 90 degrees, right? Because 2 theta is what we're taking sine of, right? So when that equals 90 degrees, we're going to have a max, meaning theta is going to be at 45 degrees, right? When the range is at its max. So, and that makes sense, right? If you shoot a projectile, right, and you want it to go as far as possible, assuming there's no air resistance, and this model right here does not take into account air resistance, but if there's no air resistance, if we're on the moon or something like that, then 45 degrees will give you the longest range you could possibly shoot, because it's going to maximize your flight time as well as your horizontal velocity. So if you want to throw something as far as possible and you're on the moon, 45 degrees. If you're on Earth, I think it's right around 38 because of the air resistance situation. Okay? But just using basic idea of what we know about sine allows us to do that. All right, so the homework for tonight. The homework for tonight is the following, and this is from a new handout which I will email out to everyone today. Have a great day, and we'll see everyone tomorrow.